Alright, so this is our honors chemistry lesson video for section 13.2. And so in 13.1 we focused on gases, and so in 13.2 we will focus on liquids. So the high kinetic energy in gases and liquids allows the particles to flow past one another. So since they have higher kinetic energy than a solid, where the solid particles are trapped in those fixed locations, liquids and gases can flow. And so substances that can flow are called fluids. Now everybody knows a liquid is a fluid, but a lot of people don't understand that gases are also fluids. Gases can flow just like a liquid can. Intermolecular forces, however, keep the particles in a liquid close together, which is why liquids have a definite volume unlike gases. So if you remember when we talked about the kinetic theory of gases, we talked about how gases, because they're so far apart and they're moving so quickly, we can assume that there are no intermolecular forces between the particles. Well, in a liquid, they have stronger intermolecular forces, so they're closer together, so they can't just expand to fill a container like a gas. Liquids are also more dense and less compressible than a gas. So if you look, the particles of a liquid are already super close together, just like a solid. They're just not orderly like a solid. So yes, they're a little bit further apart, but they're still very close. So liquids, for the most part, are not very compressible, whereas gases, because the particles are far apart, we can compress them into a smaller volume. So the resistance of a liquid to flow is called the viscosity. The greater the liquid's viscosity, the more slowly it flows. So think about something like syrup. When you squeeze syrup versus like pouring water, the syrup flows a lot slower, so the syrup is more viscous. Viscosity is related to intermolecular forces and the likelihood of molecules to become entangled. So if something has long chain-like molecules, it tends to be more viscous because the molecules are kind of like spaghetti noodles. Like they just get all tangled up with each other, so they can't flow as well. Viscosity also increases with molar mass, and for any given substance, viscosity decreases with increasing temperature due to the increase in kinetic energy. So think about syrup. If you pull it out of the refrigerator, it pours very slowly. If you heat it up, it pours a lot quicker because the particles are moving faster, so they can flow more quickly. So surface tension is the energy required to increase the surface areas of a liquid by a certain amount. The molecules in the interior of the liquid are attracted on all sides in all directions. So see, when we have a molecule that's down in the liquid, it has intermolecular forces in all directions. The molecules on the surface of the liquid have a net inward force, like into the liquid. So see, on the surface, there's no forces counteracting this downward pull. And so that causes that surface tension. And so, of course, the stronger the forces, the more surface tension it would have. So we've already talked about cohesive and adhesive forces already, but we'll cover it again real quick. So intermolecular forces that bind similar molecules together, such as hydrogen bonding in water, multiple water molecules being attracted to each other, those are called cohesive forces. Intermolecular forces that bind a substance to a surface, like a drop of water being attracted to a glass surface, like a window, those are called adhesive forces. So cohesive is molecules that are similar. Adhesive are molecules being attracted to a surface. And so that cohesive and adhesive forces, those determine what direction a meniscus bends. And so again, I know we've already talked about this, but we're just throwing it in here again. So the meniscus of water, and so I know this is kind of hard for you to see, but it's a U-shaped. It kind of goes downward. The meniscus of water is U-shaped because the adhesive forces between the water and the glass are greater than the cohesive forces between the water molecules. So in other words, the water is so attracted to the glass that it's trying to go up the edges of it. So that's what causes that upward bending on the sides. Whereas the meniscus of mercury curves downward. So it's actually like this. And that's because the mercury's cohesive forces are greater than the adhesive forces of the glass. So in other words, it's like the mercury doesn't want to touch the glass. It's trying to like run away from the glass and, you know, attract to itself. And then again, I know we also already talked about capillary action, but here's another time to discuss it again. So the rise of liquids up very narrow tubes is called capillary action. The adhesive forces are responsible for capillary action. So the more narrow the tube, the higher the liquid will rise. And again, that's those adhesive forces of the liquid being attracted to the glass, and so it's kind of climbing up the glass. So when we talk about liquids, of course, we need to talk about evaporation. So the conversion of a liquid to a gas that is not boiling is referred to as evaporation. So evaporation can happen at any temperature, but once you hit the boiling point, we refer to it as boiling. But all of them fall under the term vaporization. During evaporation, only molecules with the highest kinetic energy can escape the surface of the liquid. So when we talked about gases, we said that even though temperature is related, directly proportional to kinetic energy, if you have a sample, the temperature is the average kinetic energy. Each molecule has its own kinetic energy. So the fastest ones that have the most kinetic energy, they can escape and become a gas. Well, if the fastest ones leave, the fastest ones also have the highest temperature. So if the fast ones leave, then all you have left are the slow ones. Well, temperature is based on speed or kinetic energy, so that means you have a lower temperature. So the particles left in the liquid have a lower average kinetic energy, resulting in a lower temperature. That's why we sweat, because evaporation is a cooling process. The fastest ones that have the highest temperature evaporate and become a gas. So what you have left are the slower ones, which means less kinetic energy and a lower temperature. So vapor pressure is a measure of the force exerted by a gas above a liquid. So when you have a liquid in a closed container, some of the molecules are going to evaporate. However, eventually this airspace will be saturated, and so no more can evaporate, and so every time a new one evaporates, one has to condense. That's why you see up and down areas. And so we reach what's called equilibrium. So every time a new one evaporates, one more has to condense. A new one evaporates, one more has to condense. The pressure caused by these evaporated molecules is called the vapor pressure. So here's a picture where you can see it, because bromine is a reddish-brown liquid, but it's also kind of a reddish-brown gas, so you can actually see it. So we have liquid bromine, and so if you look, they close the lid, and so some of that bromine has evaporated into a gas. So we have liquid bromine down here and gaseous bromine up here. And so the pressure caused by the bromine molecules that are in this area, that is referred to as the vapor pressure. An increase in temperature increases the vapor pressure produced by a liquid, because of course if you increase the temperature, more molecules have enough kinetic energy to become a gas. It's kind of like if you heat a substance, it will evaporate quicker. So vapor pressure is the pressure exerted by vapor in equilibrium with its liquid or solid phase. So again, like I said, this is how we start, and the fastest, most kinetic energy, molecules that have the most kinetic energy evaporate, but eventually you're going to get to where this air can't hold anymore. So let's just pretend like this is water. The air can't hold any more water molecules. It's saturated. So every time a new water molecule is ready to evaporate, one has to condense. And so that's when you reach equilibrium. At any instant, some of the molecules on the surface of the liquid possess enough kinetic energy to overcome the attractive forces and escape to the gas phase. And so like I said, once this airspace though becomes saturated with whatever the liquid is, once it evaporates, then it has to start condensing, and that's where we reach our equilibrium. So the weaker the intermolecular forces, the larger the number of particles that can escape and the higher the vapor pressure. So if a liquid has weak intermolecular forces, the molecules aren't that attracted to one another, so it's easier for them to escape and become a gas. Now, if the container is closed, the rate of evaporation will eventually equal the rate of condensation, and equilibrium will be reached. So if the container is left open, and let's just say this is water, eventually all the water molecules can just evaporate and leave, and then you would have nothing in the beaker. But if you close it, like I said in the beginning, some's going to evaporate, so we're going to increase that vapor pressure as more evaporate. But eventually we get to the point where no more can evaporate. The air is saturated, so every time a new one evaporates, one has to condense. So eventually the vapor pressure will level out, and it can't really increase anymore at that point. So volatility. Substances with high vapor pressure, such as gasoline, evaporate more quickly than substances with low vapor pressure. So the higher the vapor pressure, the more quickly it will evaporate. Liquids that evaporate quickly are said to be volatile, and vapor pressure increases with increasing temperature. So if you increase the temperature, the vapor pressure increases because more molecules have that kinetic energy they need to become a gas. So why are we talking about vapor pressure? Well, we're trying to get to boiling point. Unlike the elementary version of the definition of boiling point, which is the temperature at which a liquid boils, the boiling point's definition is actually totally related to pressure. So a liquid boils when its vapor pressure equals external pressure. So the pressure in the atmosphere and the vapor pressure of the liquid are equal, because in that point, the liquid is not trying to fight its way out to become a gas. The pressures have become equalized, and so it can boil. The boiling point of a liquid at 1 atm is called the normal boiling point, because as pressure changes, your external pressure changes, your boiling point will change. So as external pressure decreases, the boiling point decreases, and vice versa. So this is why if you go up a mountain, water will have a lower boiling point than it does at surface, ground level, like at the ocean level. Sea level, that's the word I'm trying to think of. So also, this is the way a pressure cooker works. If you can increase pressure, then that will increase the boiling point and your food will cook faster. So let's look at an example together. So it says, use the graph to estimate the boiling point of diethyl ether under an external pressure of 0.8 atm. Well, the problem is they gave me 0.8 atm, but on the graph it's in torr. So the first thing I need to do is change 0.8 atm to torr. Alright, so hopefully you watched the last section, 13.1 lesson video, because that's when I showed you pressure conversion. Alright, so we have 0.8 atm, and then from my pressure conversion, I know 1 atm is 760 torr. So I follow my golden rule. atm is on top, so I put my 1 atm on bottom, and that equals 760 torr. If what I'm doing right now seems foreign to you, then that means you need to watch the lesson video for section 13.1. Since both numbers are on top, I multiply, so 0.8 times 760 gives me 608 torr. Alright, so we are using the graph to estimate the boiling point of diethyl ether under an external pressure of 608 torr. So here's diethyl ether, it's my first line. Here's 600 torr, so I just go a little above it. So I'm right here, and then I just come down. And so we're in between 20 and 40, but we're not quite halfway at 30. So I predicted about 26. So like when I came down, I said, okay, we're not quite halfway, but we're about halfway to halfway. So I said approximately 26 degrees Celsius. Now, of course, whenever you're estimating, you have some wiggle room. Like if you had said 25, 27, 28, any of those would have been fine. All right, so the important thing is, though, to realize that you needed to convert the pressure before you did this, because if you were looking way down here at 0.8, you wouldn't have even been able to figure it out for diethyl ether. It doesn't even go that low. All right, and apparently when I made the PowerPoint, I predicted 27. All right, so maybe pause it and you try the next one. And so then I'll assume you've done that, we'll look at it together. So it says, at what external pressure will ethanol have a boiling point of 60 degrees Celsius? So I find ethanol, so here's my ethanol line right here. We are looking at 60 degrees Celsius. So right here, and then I go across. So I'm about right here. So it looks like maybe like 330-ish, 340-ish. Torr, let's see what I predicted. Oh, I predicted 350 on here. Okay, so 350, and so again, if you're predicting or estimating, it's not going to be, you have to have the exact amount. Okay, so about 350 torr. And so again, you need to make sure you pay attention to what units you're given. All right, so let's see what I predicted when I made the power. Oh, wow, 350 torr. And I wrote it at exactly the same spot. Wow, that's pretty impressive. All right, so let's talk a little bit more about boiling point and pressure. So the rate of evaporation increases as temperature increases. So if I have a bowl of water and I put it out on a cold winter day, and I have a bowl of water and I put it out on a hot summer day, the water on the summer day would evaporate faster because more of the particles have the kinetic energy to become a gas. when a liquid is heated to a temperature at which all the particles have enough kinetic energy to vaporize, that's when it begins to boil. So see, evaporation happens at the surface. Boiling happens throughout the whole liquid because at that point, all the particles can become a gas. The temperature at which vapor pressure equals external pressure, that is the boiling point. So remember, boiling point is completely based on pressure. So because atmospheric pressure is lower at higher altitudes, boiling point decreases at higher altitudes. That's why if you ever use like box cake mix or something like that, if you look in the directions, a lot of times they'll have high altitude directions where you have to change some things, and that's just because the boiling point is different at that point. And at higher external pressures, the boiling point increases. And so again, that's how a pressure cooker works. They keep all the steam built up in here, so that increases the pressure inside, which means it will boil at a higher, water will boil at a higher temperature, and so you can cook your food faster. So, section assessment. In terms of kinetic energy, explain how a molecule in a liquid evaporates. So, the molecules with the most kinetic energy can evaporate to become a gas. The molecules with the most kinetic energy can evaporate to become a gas. Number 2, explain why the boiling point of a liquid varies with atmospheric pressure. Well, the definition of boiling point is the boiling point is when vapor pressure equals external pressure. So if external pressure changes, boiling point changes. Okay, so boiling point is when vapor pressure equals external pressure. So if if atmospheric or external pressure changes, then your boiling point changes. And last one, explain how evaporation lowers the temperature of a liquid. Well, evaporation is a cooling process because the molecules with the most kinetic energy and the highest temperature evaporate, leaving the molecules with the least kinetic energy and the lowest temperature. Alright, so hopefully there wasn't anything real new in this section that was tricky. The main thing is to make sure you really have a good grasp on vapor pressure. There's lots of good questions they can ask about vapor pressure, and so if you don't really have a good grasp of what it is, they can get really tricky.